Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so now we have to talk to people who came yesterday to the session on semantics, semantic repositories and modeling. So I believe you're going to give a more of an in-depth explanation of what the Tupelo system is today.
Yes.
And so the talk is given by Joe Futrell. I'll continue with my French accent.
Futrell, it's not actually a French name. My dishonest ancestors added the E to make the British name sound more French.
Oh,
And my great-grandfather was Jacques Futrell, who was a famous mystery writer who died on the Titanic. So I'll just get that out of the way. It's sort of my social trump card. I am going to talk actually a little bit about Tupelo, the software. And the word framework is on this slide, and I kind of apologize for that because it's for lack of a better word. As a programmer and somebody who thinks about the larger issues, I'm sick of frameworks. There's always another framework, and it's supposed to encompass everything. And what happens is that stuff gets stuck in the frameworks, and you can't move it out of the frameworks. That's an issue that I'm going to talk about. So I'm going to develop some of, let me actually start the slideshow here. I'm going to develop some of the design principles after talking a little bit about why we're doing this. I'm going to try to be provocative, and what I'm going to say, it could not be more consonant with what Joel was talking about. The approach he's talking about is what we think is required to enable a software stack and re-engineer the tools on the scientist's desktop so that we can play in this semantic space. Tupelo is based on the idea of combining the semantic web, which typically has been used to represent metadata, with the idea of content management, which is the generalized management of content objects, because when we work with scientists, they need binary files. They need big files that have lots of data in them that are in some format. That's not going to go away. We aren't going to represent those all as triples. So we need ideas from content management systems. We need ideas from the semantic web, and we call that knowledge spaces. And then I'm going to talk a little bit about some of the applications that we've re-engineered using Tupelo. Why are we doing this? Scientists increasingly want to observe and model whole systems, so multiple systems at multiple scales. The data products that need to be consumed in order to do those analysis are heterogeneous. They come from multiple sources that are otherwise uncoordinated in many cases. Especially in environmental observatories, there are sensors throughout there are multiple different kinds of sensors producing different kinds of data products throughout the environment, and when you need to model them, you need to pull together lots of different codes and tools in order to get a valid result, hopefully. And different disciplines are involved who have historically not worked with one another, so they each have a different tool stack. Here's my first provocative comment. We heard the phrase, the network is the computer, but I'm going to propose that data is the network. And one of the interesting things about data as a network is that there's no boundary to it. It's not in a repository. You don't go to one repository to find all the data that might be relevant to systems scale science. There's also no center to the network. There's no privileged data set that contains or encompasses all of the others. When you want to answer a problem, you traverse the data network and you find what you need to find because it is linked to what you need to find, because there's an association between them that people have asserted. That's the space we want our tools to play in. And so to do this, you have to design data for network effects. I come from the digital library community where data is not designed for network effects. It's designed to be stored in collections that are curated in many cases manually, where it sits there until somebody wants to pull it out, and then there's no connection to all of the curation activity. Once they pull it out, they put it on their desktop, they run it on their laptop, they do something with it. All of that activity is not connected with that single sort of static repository. So to get to network effects, we need global persistent identifiers. I'm going to say URIs because I'm a semantic web guy, but the point about URIs is not that they're URIs, but that they're global persistent identifiers. So when I move some data that has some identifiers from one place to another, the links don't break. I can still link to it even if it's moved. You also need open models which tolerate incompleteness. If I'm in one discipline, I get data from another discipline, and I only have some of the semantics in my discipline, I shouldn't reject the whole thing because it doesn't validate against my schema. I'm going to talk a little bit more about that later. We also need transparent protocols that can pass through data, and I actually have a slide about that. The concept of graceful degradation comes from the Dublin core activity, and that's a very important concept, which means that if you get very detailed semantics and you only understand some of the higher order semantics, you should be able to interpret as much as possible the detailed information in terms of those higher order semantics. And that's just saying that the semantic structure ought to be hierarchical. There ought to be multiple levels of granularity and specificity in your representations, because otherwise you're always going to be stuck at a different level of granularity than the data producer was at. We want to liberate data from applications. There are many, many applications that allow you to author data, and then it sits in that application's schema, in that application's format, and is only accessible through that application. And so the application basically creates a closed space that can't be linked to. There are local identifiers, there are proprietary formats, things like that. So code should not own data because data is more valuable than code. I say this as a programmer. All our programmers' code is going to become obsolete. But if there's an important data product in there, people will want to use it 20, 30, 100 years from now. And so if the data is not engineered so it can outlive the code, then we're going to literally be discarding data as those old applications go away. And we see this over and over again. There's a whole fascinating field of data forensics that's grown up around this. We also want to liberate semantics from code. So declare yourself. Declare your semantics. Represent the semantics as data instead of having them be implicit in the activity of the code that manipulates the data, which is another problem with the stovepipe application stack, where the application has its own data store. The semantics of that data comes from what typically in that factoring comes from the way that the code interacts with the data, and you can't extract the semantics from the code because code can't read code. We have things like the halting problem and its analogs. Here's a famous cartoon, and I'm going to put a little spin on it. In the cartoon, the man is talking to his dog and is telling his dog to stay out of the garbage, but the dog only hears the dog's name because that's the only thing that the dog can understand. So a lot of times, and this is what Joel was talking about, the computer science knowledge engineering approach to semantics is I am going to define my grand semantic edifice, my ontology, and then as a result of that, when I make assertions in that ontology, everybody will understand them. But semantics isn't what I say, it's what you hear. And the shared semantics are generally going to be minimal at scale. So as soon as we have enough players in the network, if you take the intersection of all their semantics, it's going to be minimal. And so the most important question is, what are the minimal semantics we need to enable the 80% case, the 90% interoperability case? Because we can't get to 100% unless everybody sits in a room for 10 years and comes up with a gigantic ontology and agrees on it, which we know that humans are bad at doing. Maximal semantics then are going to emerge as multiple nodes in the data network interact, and they each act on partial information, and their aggregate action enacts the maximal semantics that you can possibly get, because that's going to be the sum of all of the individual semantics of all of the nodes, because again, it's what they understand when they interpret the data that are the semantics that actually survive the movement of data through the network. So if you validate each exchange, and I get information because I'm a node in the network, and I validate it against my schema, and I only pass on what I understand, then that's discarding information. Now information can't move through the network. So we're looking for minimal semantics, we're looking for open, incomplete models, we're looking for tolerance of that incompleteness. And another message I have for programmers, I work with programmers all the time, and I say, let's re-engineer the software stack so that we use the semantic web. And the response is always, the semantic web is really hard. Well, actually, to make the semantic web work in the ways that Joel was talking about in his talk is not actually hard. Give everything a global identifier. That's actually not difficult to do. It's fundamentally not really more difficult than giving things a local identifier. You have to assign an identifier anyway. Link entities via properties of those entities. Those links are the currency of the network. That's how you get from one place to another. That's how you make this data, a tool that cares about this data, and a tool that cares about this associated data. That's how you connect them. We don't need ontologies when we're producing metadata. We make assertions. We make assertions based on properties that we know about. We don't need to exhaustively categorize all of those properties in order to simply assert things that other people will understand. We don't need complete ontologies or interpretation merely to traverse the network. Without an ontology, I can tell from an RDF statement that there is an association between two things. And that's already a piece of information and a piece of semantics. And so that idea of the complete all-encompassing ontology that I've been knocking down repeatedly, this is just another way to knock it down. And you can compare this with the linked data approach. I think the correct level of semantic activity or specificity is somewhere between linked data and OWL. Somewhere in that space, the magic happens. So Tupelo, again, I took the word framework out of my description of Tupelo. It's supposed to be a lightweight sort of middleware fabric for moving around assertions and getting around in these data networks. It's designed... wow. Okay. It has a minimal model of content, and by content I'm talking about those big blobs of files that scientists have to manage. A content item has a URI and it's a bunch of bytes. It sounds trivial, you can't do much with it, but actually just giving those things global URIs is really helpful. It has a minimal model of metadata, which is a sort of linked data style RDF. In other words, it can manage RDF even if the RDF is not stored in a triple store and even if there's no Sparkle support available. So that's our idea of a knowledge space. It's content management plus semantics. Tupelo interoperates with all of these technologies. We have a architecture that allows us to add interoperability with more technologies. Tupelo does not control your data. We're not saying we're going to give you a repository and you have to put it in Tupelo or else you can't use it. Instead, it provides this consistent API across existing triple stores. We're not going to write our own triple store, relational databases, and file systems. It has this abstraction of a context which you can wrap around part of the resources that you want to work with in a particular application. And to the context, you can attach policies and mapping and all kinds of other things that you might need to do in order to sort of get things up to the level of minimal semantics. It has declarative operators where if you want to do a query or you want to assert something, you construct an operator, you hand it to a context, and then the context decides who to delegate it to. Could be another context. Tupelo doesn't control your code. In other words, you don't have to change your object model in order to share those objects using Tupelo. Tupelo is written in Java. We can map existing Java classes to RDF vocabularies, and we do that dynamically instead of, for instance, requiring you to annotate your code and recompile. And those mappings are expressed in RDF so you can share them with other applications. So we have people developing tools on top of Tupelo that have different class hierarchies, but they can share partial information because we map that stuff to standard RDF vocabularies. The goal is to push interoperability agreements out of the coding and into the data, into machine processable metadata. And we have all kinds of ports that we provide. So if you want to write AJAX applications in simple mashups, you can do that, and you barely even have to think about the RDF when you're doing that. Some of the interesting ramifications of this is that the context abstraction allows us to transparently aggregate heterogeneous underlying sources. And so we can treat multiple distributed, independently managed sources as one context that we can do a query against. They're simple, minimal queries, but it's enough to get work done. If you have fancier query support, we provide operators for that. So if you have your special Sparkle implementation, you can pass the Sparkle query through to those underlying implementations. And Tupelo knows which underlying implementations support the certain features and which don't. The declarative operator means operations can be composed and performed against multiple heterogeneous backends. So if a backend only supports a very low level of operation, we can take a complex operation and we can split it into, we can compile it into a bunch of little operations on the fly, run all of those. So this is all designed to facilitate interoperability, not to replace your existing software stack or the way you manage data. Here are some applications with our virtual sensor application. By representing the sensors using some simple standard ontologies, we're able to create a sort of pseudo equivalence between virtual sensors and real sensors so that you can get a stream from the virtual sensor where the virtual sensor is computing its observations from other kinds of observations that are running in a workflow. So in this case, it's radar data that's producing rain gauge data for a virtual sensor that doesn't actually exist. And you have the provenance tracked for each one of these so that you know which data came from a virtual sensor and which data came from a real sensor in case you don't trust the interpolation model. The semantic document library is a document library we wrote to use in a portal. A lot of portal technologies ship with a sort of document library, and in the case of, for instance, LifeRay, that's just stored as a bunch of Hibernate objects. So they've taken their programming object model and they've pushed it all the way down into the database, and when you look at the database, it's just a bunch of integers, which is not very useful. So what we do is we map that to RDF, so we can look at documents from multiple sources in the portal. But by the same token, the notion of what a document is isn't baked into the code of our document library. So by tweaking a couple of mappings in the Tupelo context, suddenly we can browse sensors and their properties using the same tools and controls. And because users can rate and tag documents, now they can rate and tag sensors, simply because we have a different mapping that's been applied on the fly in Tupelo. Not because we had to rewrite a whole new tool for browsing sensors and adding those capabilities to it. It's like mashups, except that there's RDF behind it, so we have strong guarantees that the data will mean something when it's moved to another container. DigiDirt uses our digital synthesis framework, and it allows students to run supercomputer codes that were developed by researchers to model plant growth. And Tupelo coordinates the workflow engine and the display. And again, this is not a specialized application. The digital synthesis framework allows us to take different kinds of tools, map them to different kinds of ontologies, compose them together on a page, and provide the view that in this case the students need. Computational inference is sort of like the data blade concept from databases, where you want a simple property assertion like a sensor is in Illinois, but in order to figure out whether the sensor is in Illinois, you actually have to do some GIS stuff. And so the context provides Tupelo context provides a site at which we can interpose that kind of reasoning. So it's not a kind of reasoning that's supported by most semantic web stacks that can do first-order logic. But if we need to make the query, is this thing in Illinois, we can make the query as if it's just one triple. This thing is in Illinois. But the concept of Illinois is actually a complex polygon, and a workflow has to run in order to do the GIS computation. And so that means we don't have to deploy GIS codes everywhere to get GIS effects, because once we've extracted the semantic tag, it can move through the network, and it's just another tag, just like anything else. Next steps, interoperate with more stuff. We are tracking the open provenance model. My colleague Jim Myers and I were co-authors on that model. We need provenance, so we're going to support it. ORE compound objects are a lot like Tupelo contexts without the behavior. We can look at stored interfaces. And for the long view, we're trying to facilitate sharing and preserving data, and if I do my job right, the data will outlive all of my code. Those are some references, and I hope I have time for questions. Yes?
So this sounds fantastic. Sounds like Semantic Web to me, actually. That's another story.
Right.
Can I just go and download this?
Yeah.
Can I use it? And what actually is it? Is it a set collection of components?
It's a set of libraries primarily, and so you can use it in a desktop application. It also has a server support that you can deploy. It's written in Java, and it's modular so that you can deploy it based on the different kinds of backends that you want to use. In that long list there, we had Sesame that it supports, so you can sort of wrap it around Sesame, and it gives you the context abstraction. And you can wrap it around file systems and other things like that. It has to be configured a little bit. Mostly that's programmatic. We're working pretty hard to bring it up to a higher level of usability and configurability, sort of push it closer to the end user. Right, right. Yeah, we're in the process of productizing it because it's been a research code that sits behind the scientist-facing tools that we're developing in specific projects at NCSA.
And I love the portal stuff. So is the portal stuff also, you built a portal out of it, right?
Yeah, that's the Cyber Collaboratory portal. And what's the status of that, Jim? Is that
We're basically augmenting the library portal in various ways, one of which is replacing the document library with this one. A lot of what we're doing is setting up the library portal with this in for various communities that want to use the extra stuff.
Right, because I'm in two projects where both are using library, and they're early enough in their life to divert into using this rather than to use something else. So I'll hook up with you guys.
yeah, it's all library based. What we've done on the portal side.
We have actually eScience paper just talk about how the document library replaces the semantic resources.
So we can hook up in.
You can still deploy it into library.
Can you take your last question?
Yeah, it's just because I missed the beginning of your talk, so we may have defined it. What's a context?
A context is a programming construct inside of Tupelo, and what it does is it's wrapped around some underlying capabilities, and then you construct an operation that you want to do, pass it to the context, and the context, based on what kind of context it is, applies policies. It does identifier mapping. It figures out how to which implementation needs to run. It runs the implementation, transforms the operator, and passes it back to you.
Okay, I just wanted to know whether it was user-dependent or intention-dependent or whatever.
Yes, it's part of the architecture, programming architecture of Tupelo.
But just on a user-facing side, simple questions like which sensors are in Illinois, right? It turns out they're not so simple if we start thinking about time periods, right? Boundaries change and so on and so on. In some sense, the context is a place where most people are looking. If you're willing to agree on latitude, longitude, but you want to have a more or less complex way of figuring out it in Illinois, in some sense, the context is the place to put that inference there.
Okay.
You may share the underlying latitude, longitude store, have two different contexts that can be different views of whether it's in Illinois or not, or different contexts. So if that kind of